Alright, so the last video, I know I had it labeled as like lecture 2, and I think because some of these videos are going to vary in the amount of time, and sometimes I might make the video too long as far as an actual lecture for like a classroom. You might cover too less or too much. And so what I'm going to do from here on is just label it, title it like the video number. So the first two videos are video 1 and 2. This one's going to be video 3. And for the topic of this video, it's going to be an introduction to neighborhood. All right, this is again baby real analysis course. So this video is video 3. We're just going to go briefly covering what a neighborhood is. So previous video, we went over the absolute value and a list of properties. We went over the proofs for the following: the absolute value of A less than or equal to B, if and only if negative B less than or equal to A, less than or equal to B, and then the triangle inequality, which is the absolute value of A plus B less than or equal to the sum of the absolute values of each component, so absolute value of A plus the absolute value of B. So moving forward, so we're not going to be so, I guess, make it less tedious. We're going to assume these properties like we already know them, so that we don't have to necessarily cite them by the property letter. Because I know in the previous video when I did the proof of one of these, I was like by property C or by property H or whatever. We're not going to have to do that. We're going to assume that we already know these properties. All right, so I didn't mention this in the last video, but distance, the notion of distance, and if you have an ordered field, then you have the distance function, f cross f to f, where you have the distance, and they write it as d parentheses xy is equal to the absolute value of x minus y. And this is the standard absolute value that we're dealing with in R. So this is the distance. So in just one dimension. So we're real analysis, we're just focusing on just one dimension in this course as far as that goes. For now, later on, I guess towards after we've covered various, later on, we'll be talking a little bit into what a metric space is. So for our purposes right now, we're just going to think of the distance function as just the absolute value of the difference between two values, 2 points. So as an example, here I have the real number line, and I labeled x in gold as being -2 and y in green as being 4. And I just showed that the difference of the absolute values, so if you did y minus x, that's 4 minus -2, that gives you +6. And if you do switch the order around, you do x minus y, the absolute value gives you the same thing, at 6. So the point of that was that the distance from xy is the same as the distance from y to x. So this is sort of a symmetric property for that, and which we should already know, because we're taking the absolute value and how it's defined as far as it's always going to be positive. All right, so as an example for inequality, what does the absolute value of x minus 3 less than 2 look like? Well, I can use what we know from the previous video as far as properties, where we know that the absolute value of A less than or equal to B means you have negative b less than or equal to a less than or equal to b. So just getting rid of the equal to, so a less than b, that's negative b less than a less than b. So that's a property that we should already know at this point. So the absolute value of x minus 3 less than 2, so this will be like my a, and this is like my b. That's if and only if negative 2 is less than x minus 3 and less than 2. And that's if and only if you have 1 less than x less than 5 by adding 3 to all 3 components. So you add 3 to negative 2, that gives you 1. You add 3 to 2, that gives you 5. And then 3 to negative 3 makes that go away. So you're just left with x isolated in the middle between the two inequality signs. So this is the same thing. So it's the absolute value, like the set of values x, where the absolute value of x minus 3 less than 2 is equivalent to the set of x values where x is between 1 and 5 with less than signs. And on a number line, this is what it would look like. So I have 1 and 5 as my endpoints, and I have parentheses around my endpoints. And in the middle is 3. All right, so I have the open interval. Parentheses 1 and then parentheses 5. And then we see that 3 is at the center. So I would say it's centered is 3. Now notice the difference going from 3 to 5. If we take the absolute value of that, that's 2. So the distance from 3 to 5 is 2. Likewise, the distance from 3 to 1 is also 2. So that distance 2 is called the radius. So 2 is the radius. So that's the distance from the center to the endpoint. And specifically, the set that we're dealing with, again, so these two sets are equivalent, where you have the absolute value of x minus 3 less than 2 is equivalent to the set 1 less than x less than 5. Now, when it's written in this form with the absolute value of x minus 3 less than 2, this is called a 2 neighborhood of 3. So the 2 is our radius, and 3 is the center of that open interval. And usually we'll refer to it as an open ball when we're dealing with any dimension Rn, but when we're dealing with one dimension, that's just a regular open interval for our neighborhood. All right, and that's called a 2 neighborhood, and 2 is the radius. So the value that we use for in the neighborhood as far as labeling it, that is going to be the radius neighborhood of whatever the center is. In this case, the center is 3. So the definition, so let A be a real number, and let's say you have epsilon greater than 0. Then the set S equals, and it's got V with the subscript E, and in parentheses A, so that's going to be our notation. That I'll be using, and that's called an epsilon neighborhood of A. So that's what we'll use for E neighborhood. And it's just the set of x values that satisfy the inequality where the absolute value of x minus a is less than epsilon. And a is like our center, and epsilon is the radius. So that's why I started out with this example where we have absolute value of x minus 3 less than 2, that's a 2 neighborhood of 3. Now we're talking about just any value a just being a arbitrary real number, and epsilon being this radius corresponding to that epsilon, whatever neighborhood we have around a. So graphically, this is what it looks like. And I just wrote, so epsilon is going from the center A to the end point. And again, this is parentheses. And x lies in the green stuff that's in between the endpoints. And as far as the endpoints go, I didn't write this, but you could write this endpoint, since it's a parentheses, really it's like an open dot at that spot. We don't include that endpoint, but that is the same as our center A plus our radius epsilon. And then the other endpoint on the left is our center A minus our radius epsilon. So we could think of as the neighborhood as an interval. It's an interval that's a minus epsilon, comma a plus epsilon. All right, so that's the interval format for our inequality for our neighborhood. And that's called an epsilon neighborhood around A. And again, so for the one that we did earlier, we had absolute value of x minus 3 less than 2. All right, so our 3 is the center. 2 is the radius. So we have a neighborhood V of 2 around 3. Which is the set of x that satisfies that inequality. And we can do the interval a minus epsilon. Well, a in our case is 3, epsilon is 2, so we'd have a 3 minus 2, comma, and then 3 plus 2. Right, so that gives us 1, comma 5. All right, just so that we have some specific values in for epsilon and a. Okay, so here's the theorem, and we'll actually prove the theorem in a second. But for the theorem, it says for every epsilon, so the key here is that I'm using the word every. So for every epsilon greater than 0, if you have B being an element of this epsilon neighborhood around A, then B equals A. And again, I'm underlining every epsilon. So if it's true that B is contained in this epsilon neighborhood around A for any value epsilon greater than 0, no matter how small it is, then B is going to be equal to A. So to visualize, let's see, so I wrote here, so since this is for every epsilon greater than 0, epsilon can be as small as we want. So for instance, let's say I had, this is the epsilon 1 neighborhood around A. And that's just an arbitrary, just a picture representation. So A is our center. We're using a radius of epsilon 1. And I'm just labeling it epsilon subscript 1. All right, now let's say I did another neighborhood, a different epsilon, and I labeled that epsilon 2 around A. So this case is the epsilon 2 neighborhood around A. where I give epsilon2 to be equal to whatever epsilon1 is divided by 2. So I cut it in half, the radius in half from the previous neighborhood. Now if I keep doing this, so for epsilon3 neighborhood, around A, if I cut in half the previous neighborhood, which is epsilon2, that is the same thing as cutting the first epsilon1 neighborhood by 4, so dividing it by 4. And 4 is 2 squared. All right, so epsilon3 neighborhood, I'm using a radius epsilon3, which is equal to the first radius epsilon1 divided by 2 squared. All right, because that's the same as just keep cutting it in half, dividing by 2. And if you keep going on forever, the epsilon n neighborhood would be equal to the epsilon1 divided by 2 to the n minus 1. As an example, so for epsilon4, that's going to be equal to epsilon1 divided by 2 to the 4 minus 1, which is 2 cubed. E1 divided by 2 cubed, right? Because that keeps going by our pattern, which is epsilon over 8. So we have like our string of epsilons, and let's say you had epsilon 1, and then you had epsilon 1 over 2, epsilon 1 over 4, which is epsilon 1 over 2 squared, epsilon 1 over 8, that's epsilon 1 divided by 2 cubed. And then it gets guessed that the next one's going to be epsilon 1 divided by 16, and it keeps getting smaller and smaller. All right, and this just keeps going forever. Hopefully that makes sense, that if it keeps going on forever, if we keep continually dividing it by 2, there comes a point in which we have the neighborhood has to be such that A equals B. So this is getting as small as we like. I keep dividing it by 2. So let's say like that, and then keep going, and then continue that process. So hopefully that's graphically or visually that appears that if you do that, then it must be that B equals A, since it has to be true that this is for every epsilon greater than 0. Now this isn't a proof, this is just a picture sort of explaining some of the logic behind the theorem, and I thought it might help to give some kind of example where I'm specifically using epsilon divided by 2, keep dividing it by 2 from the previous epsilon. You could have used a different value. I could have divided by 3. It'd be e over 3 to the n, doing it like that. Now for the proof, I'm actually going to do a contradiction proof. So the actual proof. So we're going to show need to show that for every epsilon, if B is in the epsilon neighborhood around A, and that's for every epsilon, then B has to equal A. All right, that's what we need to show. So that, and I'll just use a different color for the actual proof, but I figured red, that's what we're trying to show. Now for the proof itself, let's, so we have, there's 3 possibilities, right, for B. You could have B less than A, or you can have A less than B, or you can have B equal to A. All right, it's by trichotomy. I'm not sure how you spell it, so sorry for the misspelling, but it's by trichotomy. I know that's not spelled right. All right, so for the three possibilities, if I test out the first two, if we test the first two cases, and we see that this doesn't work, and I'm just putting that in quotes by what I mean by this doesn't work. And so if we see that it doesn't work for the first two cases, then it's got to be the third case, B equals A. So it must be true for B equals A. All right, and this is sort of like what's going on in my head. So if we test for the first two cases and we see that it doesn't work for those, then it must be true that it works for the third case. So I'm going to do the first two cases and show that it doesn't work. So this is going to be a contradiction proof. All right, so I'm going to actually do the A less than B one first. So this case, again, we're going to assume that for every epsilon that B's in the epsilon neighborhood, but in this case, let's assume A is less than B. Now I'm going to choose, since it's true for every epsilon, that B is inside of that epsilon neighborhood around A, then I can pick any value that I want for epsilon, since it's going to be true. So I'm going to pick epsilon equal to B minus A over 2. And you'll see why I do that. All right, now, since B is an element, sorry, so it's true that B is an element of the epsilon neighborhood around A. Pick epsilon to be B minus A over 2, which we know that's positive because A is less than B. Or B is greater than A. So B minus A is greater than 0, which dividing by 2, that's also greater than 0. All right, so I'm going to try, I'm picking this value for epsilon, and I'll show that I'm going to arrive at a contradiction. Well, if B is in A, or in the epsilon neighborhood around A, and the epsilon neighborhood is the set of x values such that the absolute value of x minus A is less than epsilon, then the absolute value of B minus A has to be less than epsilon. All right, because that's just by definition of the neighborhood. So if B is an element of that neighborhood, then we have the absolute value of B minus A less than epsilon. and that's true for any epsilon. So it's got to be true for the epsilon that I chose. So in this case, by the epsilon I chose, it's b minus a over 2. Well, we know that the absolute value of b minus a is just b minus a because of the fact that, sorry about that. All right, sorry, phone rang. So the absolute value of b minus a is less than epsilon, and the epsilon is b minus a over 2 that we picked. Well, the absolute value of b minus a is b minus a, because we know for the absolute value of x is equal to x, if x is greater than or equal to 0, and then negative x if x is less than 0. Well, we know the absolute value of b minus a, it's either going to be b minus, it's going to be b minus a, since we had, our assumption is a less than b, which is like b greater than a. Okay, and then otherwise it'll be the negative of b minus a if we had b less than a. All right, so essentially I can just drop the absolute value signs. So I just have b minus a. All right, so then that's saying I have b minus a less than b minus a over 2. And I could get rid of the b minus a on both sides, because that's not going to be 0. So I could divide both sides by b minus a, and then I'll have 1 less than 1/2, which is absurd. So this doesn't make sense. So that's a contradiction. All right, so I ruled out case 1. Case 2, and that was doing the a less than b case. So we've ruled out this case. Now we have the b minus a case. All right, so this time assume b is less than a. And I'm going to pick epsilon. Instead of it being b minus a over 2, I'm going to do a minus b over 2. So I just, all right, so we know b is in the epsilon neighborhood around a. So then that means absolute value of b minus a is less than epsilon, and our epsilon is a minus b over 2. Well, since a this time is greater than b, so you could think about it 2 ways. I can switch the inequality sign, or sorry, not switch the inequality, switch the order, so it's the absolute value of a minus b. We know that's equivalent. But this, yeah, I'll go ahead and do that. So we know we can do this. All right, because it's symmetric. Absolute value of x minus y is equal to absolute value of y minus x. And then the absolute value of a minus b is just a minus b, since a is greater than b. So this is like the first case, all right? So it's a minus b less than a minus b over 2. Divide both sides by a minus b, since that's not 0. And you have 1 less than 1/2. All right, contradiction. All right, hence I ruled out the first two cases, so it must be that B is equal to A. All right, so proof's done. So if we've ruled out that B is less than A and A is less than B, so it must be that B is equal to A. All right, and I usually do that to indicate the proof's complete. All right, so I'll probably be that a little bit more, a little longer than necessary because it's not that complicated of a proof. But I thought it might help to discuss the thought process and emphasize that the key to this theorem is that it's for every epsilon, where B is in that epsilon neighborhood around A. So that for every matters here. So I can keep shrinking it down as small as I like, and then that's going to imply that B has to be equal to A. All right, so that's where I'll stop it for this video, and this was video 3. Now, next video, I'll actually begin talking about supremum and infimum. So sup and inf, what those mean. All right, so I'll see you in the next video.